Everyone, so we're going to continue our journey through chapter 13 of Steck. So this is based on Steck 13.5. Hopefully you see that here. It's going to talk about a little bit more of an overview of how you think about designing a circuit now that we have both combinatoric logic and sequential logic that can be meshed together and interact with each other, and how we can actually design circuit around using both of these. And basically this turns into what a general use microprocessor or even a dedicated processor such as a GPU will be doing when you're designing a circuit that makes allows you to process data, have inputs and outputs, and be able to do logical, operations that are much faster than what you can do in software. So this is still hardware logic that you're doing. Just a reminder, right? A combinatoric logic, so it's the adder, the multiplier, the multiplexer that we dealt with before. When you have sequential logic, you're dealing with these counters, shift registers, computer memories that you can store things that you can take to the next stage, right? So you can do one calculation, remember the previous one, and then, or even the ones previous to that, and then, you can go into infinity and how many um, clock cycle back you want to go to, okay? And the way you think about this is that there's this connection between the combinatoric logic, right, which is where a lot of computation happens. So this example of this, not just in our FPGA, but also mostly your microprocessor that's in your computer or your phone. Most of the logic in there are these combinatoric logic. That way it can do computation, okay? Where the sequential part, right, is the memory where you can remember things, and then you can feed that into the combinatoric logic, and therefore allows you to get the results from your previous calculation so you can keep iterating on things, okay? This is kind of a high level, meaning high as in, kind of zoomed out. Like, if you're zoomed out, if you're very high in altitude, you see a lot of the land, but you don't see the details, right? In this section, the book also mentioned the programmable array logic. Hopefully this sounds familiar, right? Because the stuff we've been dealing with is the field programmable gate array, which is basically a much more expansive version of a programmable array logic. There's also a programmable logic array, logic device. I think that's what the D stands for, right? So these are basically a little bit more primitive version of FPGA, where the FPGA has a little bit more to it, because not only does it have the combinatoric logic and the memory, it also has like little dedicated memory banks that you will not see in a PAL. You also will not see like simple interfaces like dials, these switches and that you see. Um, these are often more application specific. So for example, you'll find these like in like your thermostats, your car. Where else have I seen these? Like a little the gas heater, right? The gas meters that you use. These are all programmable array logic where you can, update the 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 hardware, so that you can do different things. You can reset the data if you need to and stuff like that. So they tend to be much simpler. So in our class, we'll only focus on using FPGAs, which is what we've been using in our lab too. So, but the book has a really cool example of using this to do a divide. This is known as a divide by three counter. So why, what is this divide by three thing? Let's describe why it's needed sometimes, okay? So going back to the previous lecture, we talked about the slow clock, right? Where we can, if we have a start off with 100 megahertz clock, right? We can divide that to make it um, a you know, 1 megahertz clock by counting up to 100, right? And then resetting the clock. So this is easy if the frequency of the clock you want to make is factors of 100 million, which there are many. But for example, exactly 33 megahertz clock is not one of them, right? So this allows you to divide things by 3, which is kind of neat. Okay, so this is a little circuit that has 2 D flip-flops. Okay, your clock comes in to both, just usual. That just sends the data from D, for whatever D is, to the Q, right? It just sends the data forward. There's no connection to Q bar, so we don't need to worry about that. Okay, so that's why it's not on the diagram. Not that they don't exist. They still exist on the flip-flop, but we just don't use it, so we don't draw it. Okay. And there's just a NOR gate kind of stuck between them. And okay, so this is a NOR, right? So the NOR gate truth table is that only if 0, 0, 1, 0, 0, 1, 1, 1, right? So an OR gate, right? If either input is high, then it goes high. But the NOR gate is opposite of that, so it's just 0, 0, 1, 0. Okay, sorry. So let's just read it from top to bottom. It's 1, 0, 0, 0, 0. Okay, so the only time that the output is high is when both inputs are 0, right? Because that's when the OR gate is 0, but you take the complement of that. Okay. All right, so let's see how this circuit works. Okay, so you have a clock coming in. Okay, let's first assume that all these outputs are at 0. So I'm going to do this once again, this little colored um, timing diagram. I mean, it's basically shown in this table here, but we'll do it on the circuit so we can see it. Okay, so what happened is that, right, notice that this Q1 feeds all the way back to D0, so that means the first state that D0 is actually going to be 0. But it also feeds back with a split connection here to this NOR gate, so this is 0. So 0, 0 on a NOR gives you a 1. Okay, so therefore the initial state, right, if we start off with Q0 and Q1 both equal to 0, what happened is that D0 is 0, and then D1 is actually 1. Okay, hopefully that makes sense up here. All right, so let's say this is a positive edge, so when the clock goes up, right, what's going to happen is that the data from D gets sent to Q, right? Since in this case, right, D0 is 0, Q basically gets changed to 0, right? Let's just write that, right, comma 0. Okay, so well, that didn't do anything, but right, D1 gets sent to Q1, so therefore this actually changed to 1. Okay, now this feeds back up to here, right, where it just switches this to 1 and switches this to 1, right? And now it's different, right? Let's check this. What's the output of this gate now? Okay, so the output of this gate, right? It's a NOR gate, so it switches instead of being the output being 1, it switches to 0, right? And now, right, D1 becomes 1, D0 becomes 1, D1, I should have wrote that, give myself a little space here. Start off at 1, right? It switches to 0, right? Because now that's in this state, yeah. Okay. And then so the rest will stay the same. Okay. And now, right, so that's what the state is. Okay. What happened next, right? So what happened is that the output here pulse high once. Okay. And let's see what happens after the next clock cycle. Okay, so just as before, right, when the clock pulses from low to high, let's do that in blue now, right, it sends whatever is at D over to Q. So this gets sent to, since this D is 1, it goes to 1 here, the 1 goes here. And then since this is 0, this goes to 0. So now the output here goes low. this propagates back to here, right? This goes to 0, this goes to 0 because this are hardwired, right? Okay, so now, okay, the output states, oh, the inputs and output states becomes, oops, I forgot one more step, right? I didn't have a blue here, right? So this is 0, 1, so the NOR of that is still 0. So we keep that, okay? So now on the third step, blue, right? Q0 is 1, checked. Q1 is 0, and then both D's are actually 0. Okay, let's do one more clock cycle. Okay, I guess we'll go to black then. Okay, so once again, right, whenever the clock goes from low to high, it goes, the D goes to the Q. So whatever, so this started out at 0, so this goes to 0. Okay, and then this starts it off 0, it goes to 0. Okay, and now this propagates back here to be 0, 0, so nothing interesting. So what happened is that basically everything stays almost in the same state, but right, it's a little bit different, right? So D0, so let's check the Q's first, so we can go here. Q0 is 0, right? Okay, and then Q1 is 0, okay, and then D0 is still 0, but then D1, right, since I didn't, once again, right, so I did not do the last step. I always forget this last step. Right now the input is 0, 0. That's actually a NOR gate that gives you a 1. Okay, so that's the difference. And now you notice that is actually exactly the same as the beginning state, right? And then so this cycles through. So every 3 clock cycles, it does the same thing over and over again. So therefore, after 3 clock cycles, what happens is that the output goes high. After 3 more clock cycle, output still goes high. So this allows you to divide by 3. So if you put in a 100 megahertz clock, you get 1/3 of that, or 33 megahertz clock. Okay. So this is sort of an interesting little circuit, and it's a good example to demonstrate how combinatoric logic, right, which is literally just this NOR gate here, right? The NOR gate is the combinatoric, not let me just write it, right? The NOR gate is the combinatoric logic, right? While the 2D flip-flops are the sequential logic. And then the information from the D flip-flop is being fed back to the NOR gate, and then the NOR gate is feeding information back to the sequential logic to the D flip-flops. So it keeps interacting with each other. And this is basically how your computer works. Okay. So I was going to have you guys write this yourself, but let's just, since this is the first time out, let's just implement this line by line, and I'll describe how this works. Okay, so you may want to implement this in Verilog, right, as opposed to wiring things up. You can if you wanted to. So what's done here, let's do that in, let's highlight that in green, right? So what I do is I declare these wires basically to be exactly the same names as what we saw up here, right? D0, Q0. I didn't do the capitalization because I didn't want to push shift when I typed these in. Okay, but the thing that's important is that D0 and D1 can be wires because they are not registries, right? They are wires that are connected from the output of those registries back to the input. Okay, where Qs, they have to be declared as registries because they are part of the sequential part. Okay, and then the combinatoric logic is that, well, let's see, I should have drew the diagram. Let me just draw the diagram real quick. Okay, you have D0, Q0, and this goes through a NOR gate, and then you have D1, Q1, and this goes back to the input here, and also to the output here, and then you have the clock coming in to both. Okay, very simple logic. Okay, this is a uptick clock. Okay, so what do I do here? So QD0 equals to Q1. So basically the wire of D0, I'm going to highlight that wire here in yellow, right? Well, I guess I'll do it in, in green, right? That's this wire. It's physically there, okay? And then when you program the FPGA literally just use electric field to hold those wires. Well, it's actually using transistors in order to open and close wire gates, but it's essentially electric field at the end anyway, right? This is creating that wire, okay? And that wire also goes to this NOR gate, right? That's not the all of that has the same voltage. Whatever current, whatever voltage you have there is going to be the same, right? Okay, so that's this line. Okay, and then the other combinatoric logic. Actually, going to really do it in yellow this time. I really mean it, because right is that whatever D0 is going to be not the OR of Q1 and Q0, right? So why is that, right? So the NOR gate is here, right? One of the input is Q0, so that checks out, right? That makes sense. But why did I put Q1 here? Remember, Q1 goes all the way back up here, right? Q1 is equivalent to D1. So in this line here, I could have wrote sorry, Q1 is equivalent to D0. I could have just wrote D0. Either way would have worked, okay? For Q1, you can replace Q1 with D0 because I made them the same in a different line, okay? Right, notice that I'm not saying previous line, okay? This is not software programming where things get read out line by line. This is wires that are being made permanently. Well, as long as you run that program on the, as long as that FPGA is programmed with those particular wire sets. And then yeah, of course, D1 goes all the way in here. Okay. Right. So that's the combinatoric, it's two lines, okay? The sequential logic is that, well, whatever D0 is, it has to get forwarded to Q every clock cycle, which is what this does, right? And then whatever D1 is, it has to get forwarded to Q1, which is what this line is. So that's the sequential part of the logic, okay? And I want you guys to write your Verilog code like this, because it breaks up into some declaration, some combinatoric logic, some sequential logic, okay? And then we're going to output, you know, Q0 and Q1 to LED just to make sure that, you know, one of them blinks 3 times faster than the other, okay? This makes it easy for human to understand it. Your FPGA does not care, because what happened is that when you synthesize, implement, and bitstream this, all of this will happen all at the same time, okay? So you don't have to do things in order, right? It's not going to do things in order. It's actually doing it all at once, okay? So this little circuit actually brings up a little fun functionality in Vivado, which is the schematic generator, okay? So remember that synthesis, when you synthesize your code, right? It takes your Verilog code and basically makes it into a circuit. That's what synthesis does, right? You can actually see this, okay? When you after you synthesize, you can open the synthesized design, okay? And you just click on the schematic. And then on that schematic, it pops up like this. You can physically see the 2D flip-flops. I guess I can just write, right? You can see the 2D flip-flops that we made on the in the Verilog. And this one is LUT, is logical unit transistors. I think that's what T stands for. It doesn't label what it is, but obviously this is the NOR gate that it made for you. Okay, and it has some outputs from some to LED. So one of the things, maybe I would point this out, right? Notice that it looks like both of these output went to the same LED. It's not, right? This is a vector of LED from 1 to 0, right? So therefore, it's actually two LEDs that I mapped to. I think you can actually click on this to expand this if you want to see individually which LED goes to which. And therefore, you can actually check all your wires, right? Make sure that your wire, what you wrote in the code is actually what's in the diagram. It's not going to look exactly the same, of course, right? But this will allow you to visually inspect things so that you can actually see if one line of code is not correct. Notice that the clock here went through a couple of buffers. This is one of the things that you will notice if you start doing stuff that's very fast, that the clock is a device inside FPGA. In order for that to be useful with your um, inside your circuit, inside your FPGA, it has to be buffered. That means what happens is that the buffer actually holds that information for one clock cycle. So therefore, the clock, even though the oscillator can be going up and down, whatever speed, whatever each of your clock cycle is going to hold that. And in this case, I think it's 10 nanoseconds because you have a 100 megahertz clock. Okay. Yeah, and these are called FDRE. Stands for flip-flop D-type reset type enabled. There's just a lot of naming convention in there. Okay. Next, so hopefully that makes sense. How you can synthesize these things and then actually see the diagram, which is a pretty good feature, cool feature. All right. The next one I want to think once again a little bit more high level again, right? And there are these state diagrams. Okay. Instead of making a truth table, you can use a state diagram to kind of figure out what the process is when you're designing a circuit. So in this divide by 3 counter, right, whatever the inputs are, and these are the inputs, yeah, these are the inputs, right? If you start off at 0, 0, what happened is that the next clock cycle, it'll go to 0, 1, those inputs. And then next clock cycle, it'll go to 1, 0, it does a little flip-flop thing. But then the next cycle, it goes back to 0, 0. Okay. Notice that the state 1, 1, where both of them are high, right? That is outside this loop. And the circuit is actually designed so that if it is at 1, 1, it'll go back in here. But this is the unused state, right? Because in the divide by 3 counters, you actually want the counter to reset every 3 clock cycles. So 1, 2, 3. And that's why you don't need that fourth state, okay? Even though it's not needed, you should always make sure to design things so that that unused state takes you back to the useful state in the cyclic state. Because what happened is that if this line didn't exist, you would just be stuck at 1, 1 all the time, and your program would just hang. Your circuit would just freeze. We're not doing anything. Okay. Another way to think about this is also you can do this counter. Instead of counting up, you can also count down. So this is kind of like a design where, oh, if I want to count, I want these are the outputs, right? Q0, Q1, right? If I want those to start off at 0, 0, if I want to count up, meaning I'm going to have a little switch called U, right? If up is equal to true, right? U is equal to true, then I want to count up. So the next state I want is 1, 1. The next one is 1, 0. Sorry, not 1, 1. The first state is 0, 1, and then 1, 0, and then 1, 1, and then it's back to 0. So, and this is how you count up. But, right, if you want to count backward, meaning I want to count up, I want the up key to be false, right? That means U equal to 0. What happens is that when you go from 0, 0, it actually goes to 3 instead, or 1, 1, right? And then 2, 1, 0, or 1, 0, 1, and then it counts down instead. Okay, so you can have a little key like that. Okay, This can be done. Um, I think that's the up-down example that we can play with in the pre-lab. But for the 3-bit counter, right, the way you would program, well, register, you code in the wiring for these, or physically put on your breadboard, is by basically adding a multiplexer to your inputs. Okay, so how do you do this? In case this is the 3-bit counter, right? Still, not this one. Okay, okay, okay. So what you would do, you would just add a multiplexer to this, right? Let's say, right, and then you would just have, a in this case, it's going to be H for hold, right? So if hold equals to 1, right, then what happened is that, oops, sorry about that. Hold equals to 1, right? And you tie this to ground. No, you don't tie that to ground. You tie this to itself. You tie this over here, tie this to itself. What happened is that if hold equals to 1, it'll select this input for D0. And what happened is that, well, it's just going to make D0 equal to D0, so nothing happens. And then you can do the same thing here where you add a, oh, how did I change to black? Right, you add a multiplexer here, right? And once again, this connects to itself, right? So if your holds the select key in your multiplexer, right? This is here we used to use SEL for that, right? If hold is equal to 1, then you just basically keep putting in the same input as opposed to letting the other input go through. Okay, but if hold is equal to 0, then it just operates normally like you had before. Okay, and this way it allows you to like control the inputs and outputs to your combinatoric logic, which is very important, and we're going to see that when we talk about um, kind of the conceptual design of a microprocessor and how your computer actually work in the next lecture. Okay, so that's all for this part. I will see you in the next lecture.